Yes, so you can just click got it. So perfect. Do you want to
Ben?
stop sharing your screen for a moment, Ben? Oh,
Ben, since you have these slides, do you think you could share them?
Certainly.
Good. That will make it less necessary to take notes.
I totally understand that.
absolutely. And it will also be recorded. So we will be able to share. We'll be able to share the recording
Okay,
as soon
thanks.
as soon as it's done.
We're going mute again.
Perfect. Everyone except for me, and then I will mute. Let's mute so we can make sure that we give Ben all of our attention and we're not distracting. I don't know most of the people because I started early January, but my name is Yael Friedman. I'm the Senior Director of Philanthropy, and I oversee our major gift team, which includes our Visionary Circle and our amazing major gifts. So I got to come in at the tail end of the exceptional Victory for Vision campaign. We're so grateful to everyone who invested their time, their energy, their treasure into moving forward the most innovative and exciting research. I'm really, really proud to be part of this organization and to work with our team, and very excited to highlight Ben, who makes science relevant, accessible, and super interesting. I think that's all of my intro. Most of you know Ben well, but Ben is our VP of Science Communication, and he's utterly brilliant. Ta-da!
Well,
Take it away.
Well, thanks to all of you out there across the country and maybe beyond the country for joining us to learn a little bit about what happened at ARVO this year. And for those of you, I know there are many on the call who totally understand what ARVO is. For some of you, you may not be that familiar with ARVO, though you've heard the acronym talked about quite a bit over the years. And so I'm going to actually start out by telling you a little more about ARVO and this big annual meeting that we're always so excited about. But what I will say as far as questions, I think it'll make the most sense to answer questions toward the end. So if you can hold off and write your question down, you could put it in the chat. If I go straight through these slides, it should take me about a half hour. So we should have plenty of time for questions as we go. So to kick off, as I just said, wanted to let you know a little more about ARVO. So ARVO is the acronym for the Association for Research in Vision and Ophthalmology. This is an association, much like a lot of professional associations. They have a number of benefits and activities. They have journals. They have education and career development. And they also have their big annual meeting. And that's really what those of us at the foundation get most excited about, is the big ARVO annual meeting. It's held either in late April or early May of every year. And the most recent meeting was in New Orleans a couple months ago in April, the 23rd through the 27th. Now, before COVID hit, ARVO attracted up to 13,000 attendees from around the world, international attendees. And then during COVID, there was a year or two where it was just virtual. And now things, since we're opening back up, attendance is picking up again. And we had nearly 10,000 attendees in this past year. And attendees are researchers, doctors, industry professionals, and just about every member of the foundation's science team. And really, what happens at ARVO is there are thousands and thousands and thousands of research updates. And while we're, of course, interested in research for inherited retinal diseases and dry AMD, ARVO covers the entire eye, front of the eye, back of the eye, the middle of the eye, glaucoma, vitreous, the whole eye. Now, my colleague, Amy Laster, who heads up our grants program, she always does an analysis with the ARVO people to figure out how many research projects that are presented at ARVO were foundation funded at some point. And this year she came up with at least 80 projects that had foundation funding. Now that number is probably low because there are investigators out there who aren't so diligent about indicating their funding sources, but at least 80 projects, again, were funded by the foundation. So we're very proud of that. So what happens at ARVO? How is the research presented? Well, one of my favorite ways to learn about research are the posters. And so every day at ARVO in the exhibit hall, they have thousands and thousands of posters along these long aisles. And what happens is researchers stand by their poster, the poster reflecting whatever project they were working on. And you, as the attendee, as the visitor, can walk by and look at the poster and have a conversation with the researcher about the research. Sometimes you're talking to people you know well and you're just kind of catching up. Sometimes you're learning about new research and you're meeting a new young investigator. That can be really exciting. But I find the poster presentations really, really enjoyable and informative. And in addition to posters, there are hundreds and hundreds of typical presentations where people are showing their work from PowerPoint slides. There are a lot of panels that do Q&A. And we, as a science team and the Retinal Degeneration Fund, our venture philanthropy fund, we have a lot of meetings with partners and research groups. Since everybody is at the same place, it's a great time for us to get together and talk about deals and research initiatives and just catching up on what each other is doing. And so, yes, we learn a lot about research at ARVO, but the networking is really, really a big part of it. So one thing that's really exciting and becoming uber popular is a summit that we hold 2 days before the official conference starts. So this year it was on Friday, April 21st. And this summit is known as the Gene and Cell Therapy Innovation Summit. And we co-host this with Oregon Health and Science University. This is the 8th year that we've done this. And it's a one-day summit focused on gene and cell-based therapies, a lot of other clinical trial stuff. And this year we had 30 talks. I mean, it was a jam-packed, chock-full day of information. Each talk is about 15, 20 minutes. And it was a really great update on what's happening in the clinic and things that are moving toward the clinic. We had a special focus on clinical trial design and endpoints this year. And again, we had 300 attendees. This event, people pay to go to this, and it sells out very quickly every year. And I'm happy to say, to offset the costs, we got a number of sponsors, 15 sponsors, and really the whole science team is involved in putting this together, organizing it, moderating the sessions. I do a very comprehensive write-up of all the sessions. It's on our website, and when I'm done here, I'll put a link to that summary in the chat. So that's always very informative for me, because I sit through the presentations and I learn, but when I go back and actually do the write-up, that's when I really learn this stuff. And again, that summary is on our website. Again, I will put the full link to that in the chat. So one thing that ARVO features every year are a handful of prestigious talks where researchers are awarded medals or awards for the great work they've done, the great careers they've had in research. And this year was really special for us at the foundation because Eric Pierce at Mass Eye and Ear and Harvard won the Proctor Medal, very prestigious award. And for those of you that don't know Eric, he's been with Mass Eye and Ear for a number of years. He was at University of Pennsylvania, Shea Eye Institute. Officially, he's the director of Mass Eye and Ear's Ocular Genomics Institute. But for those of you that do know Eric, there really isn't another researcher or few researchers who are so well regarded and respected as Eric. I call him the scientist. He knows so much, he's so insightful, and whether he's presenting his own work or reflecting on somebody else's, he always has really pithy and insightful things to say about the research. Eric, in many ways, is a soft-spoken guy, but when he talks, everybody listens, like that old commercial, E.F. Hutton. Anyway, a little history on Eric. He was head of our scientific advisory board from 2005 to 2015. He had the role that Jackie ultimately took over, Jackie Duncan. He's gotten significant funding from us over the years for a number of projects. He was an investigator on the Luxturna trial at Children's Hospital of Philadelphia. As the head of the Ocular Genomics Institute at Mass Eye and Ear, he's done a lot of work in gene discovery and finding those elusive genes and mutations. And currently, his group is part of a consortium that's searching for those hard to find genes and difficult to find mutations so we can better genetically diagnose people with inherited retinal diseases. He's been involved in development of several genetic therapies, including those for PRPF31, NMNAT1, RP-GRIP1, and CEP290. And he has a particular expertise in what we call ciliopathies. And we may not think of this, the retina in this way, or photoreceptors in this way, but photoreceptors are these sensory cells that can be categorized as cilia. They're long cells that sense light. And the top part of the cell, the outer segment, the light sensing portion, can be thought of as a cilium. And so a lot of retinal diseases occur because of issues with the ciliary function, as I say, the movement of proteins and molecules up and down the outer segment, the movement of proteins into the outer segment, and you need the cilia to operate properly and to have formed properly for vision to work and for the retina, for the photoreceptors to survive. So he's done a lot of great work to understand ciliary function. Now, Eric, for his Proctor Medal lecture, highlighted a few different research projects, but he really put a focus on the CRISPR-Cas9 trial, gene editing trial, a phase 1/2 trial for people with LCA10, specifically those who have a specific mutation in the gene CEP290. LCA10 is caused by CEP290 mutations, but this particular trial focused on an intronic variant called IVS26. One thing that Eric really brought to our attention and everybody's attention is what an historic milestone this was. This was one of the first in-human applications of CRISPR-Cas9 gene editing for any part of the body, not just the retina, but the entire body. And so this was just the launch of this trial was an historic milestone. And just so you understand what CRISPR-Cas9 is, we often talk about gene therapy, replacing the gene, the defective gene with healthy copies. this is going in and cutting out and pasting in a new piece of DNA to replace the mutated region. So you can think of it as molecular scissors. Again, you can just cut in some cases. Sometimes it's cut and paste. So what Eric reported, and this had been previously reported, but he noted that about 12 of the 14 patients in the trial had improvement in at least one visual function measure, either best corrected visual acuity, their ability to navigate a mobility course. They had improvement in retinal sensitivity as measured by full field sensitivity, FST, and also they completed a questionnaire that talked about their activities and ability to see. Now, unfortunately, Editas decided not to move this trial forward. And of course, that's what we want. We want these therapies to move forward toward FDA approval. But as Eric really tried to drive home, is the fact that we even had success in this trial is important to recognize, being such an early trial for CRISPR-Cas9 technology in the retina. And Eric continues to work with Editas to find a partner to move this therapy forward. Nonetheless, CRISPR-Cas9 continues to move forward. We at the foundation are funding some CRISPR-Cas9 research projects. And there's a lot that we're learning from this clinical trial, whether this therapy moves forward or not, but a lot that can be applied to future CRISPR-Cas9 projects for the retina. So a very exciting lecture. There must have been at least 500, 600, 700 people at this lecture. It was really exciting to see Eric get recognized. So another project that I am really excited about is optogenetics, and specifically what we call cone-based optogenetics. Now, normally, and I will talk about a couple of other optogenetics projects in this presentation, but normally what we think of when we talk about optogenetics is we think of using bipolar cells or ganglion cells as like a backup system for people who have lost all their rods and cones, or who have lost most of their rods and cones. And that's where most optogenetic therapies are being applied. But Hendrik Scholl, who used to be at Wilmer and is now over in Switzerland at the Institute of Molecular and Clinical Biology in Basel, IOB for short, he and his team did a natural history study of people with advanced RP. And what they observed is many of these folks, even though they've lost a lot of vision, have what we call dormant cone photoreceptors. These are cones that have lost their outer segments. They've lost their light sensing ability, but the cell body still is surviving. So we call these dormant cones. And it's a surprising number of these folks, even with advanced disease, who have these dormant cones. They even did some post-mortem studies of people who had passed away who had advanced RP and a lot of vision loss, and saw that many of these folks had dormant cones. And the belief is that these dormant cones may be a really great target for optogenetic therapies, because cones are the cells that normally process light. They're further up the chain when it comes to visual processing. So we think that perhaps if we can bestow light sensitivity to these dormant cones, we're going to get the best response using an optogenetic therapy. Excitingly, Hendrik and his group are pursuing a cone-based optogenetic therapy. They haven't announced specific details yet, but our partners, Sparing Vision, we're investing in them through the RD fund, they have announced that their cone-based optogenetic therapy should be moving into the clinic sometime in 2024. They're going to file an IND, at least that's their plan, in 2024. So this is great information that was presented by Hendrik, and it's exciting to see that there are projects leveraging these dormant cones moving into the clinic. So another project that I was excited to learn a lot about was from Jean Bennett, our Luxturna visionary. And as I think a lot of people on the call know, Jean and her team at Spark, including Dan Chung, came up with a really innovative endpoint for measuring visual function in the Luxturna trials. And we call that the multi-luminance mobility test, the MLMT, or the maze. And this is where people with advanced vision loss go through this obstacle course where you can vary luminance to see if they can navigate better and navigate under less light after treatment. This was a really crucial endpoint in measuring vision function because a lot of the traditional endpoints, like looking at lines on an eye chart or measuring visual fields, are just not great for clinical trials of inherited retinal diseases. So what's exciting is Jean has moved even a step further, and along with her colleagues at the University of Pennsylvania, is developing a virtual reality system to measure visual function. This would be like a headset, if you all are familiar with virtual reality, you would wear, and this would be a way for somebody to navigate a virtual setting or a virtual obstacle course. And virtual reality, while the maze is a great thing, virtual reality even offers more advantages and benefits over the maze. First of all, virtual reality, the headset is just something you wear, so you don't need a big room to set up your course. Virtual reality is much easier to reconfigure and switch around because it's all done in software in the computer system that's part of this. You can configure virtual reality to measure certain visual experiences based on disease. As we know, people with RP have more peripheral and night vision issues. People with Stargardt disease, macular conditions have more central vision loss. So you can configure the system to specifically measure those different visual experiences. You can have a lot more obstacles that can be programmed in, and real life obstacles like skateboards or an open cabinet door. And Jean said that you can control the luminance a lot better in virtual reality than you can in the maze. And finally, when investigators in a trial are having somebody navigate the maze, the multi-luminance mobility course, there's actually somebody videotaping that person's experience, that person's test, and it's sent off to a reading center to grade how fast it took somebody to go through the course, what they ran into, the luminance levels, that whole scenario. Well, with virtual reality, you don't need a reading center because all that is captured in the software of the system. And so excitingly, Jean and her team are not just developing this, they have plans to launch a company to commercialize it and make this something that would be hopefully widely available. And while I don't get into outcome measures and endpoints much more in this particular presentation, that's a really key aspect of moving clinical trials forward for us and getting treatments across the finish line. We need better endpoints. So I think this is a really exciting development with a lot of potential for getting more treatments through clinical trials and across the finish line. So next, I wanted to talk about Etsena Therapeutics, a gene therapy company that got a lot of attention at ARVO, and honestly, they got a lot of attention before and after ARVO as well. So Etsena is a company that was kind of spun out of the University of Florida with Shannon Boy and her husband as co-founders. Many of you may know we've been funding Shannon for many years for her innovative development of gene therapies. She's been a wonderful investigator doing great work. And she and her husband launched their company, gosh, it's got to be a year and a half, 2 years ago. And their first project is a gene therapy for LCA type 1. That's a form of LCA that's caused by mutations in the gene GUCY2D. Like all forms of LCA, this is a severe retinal disease that affects kids. But excitingly, these kids, even into adulthood, they retain some retinal structure, even though they have very significant vision loss. So that makes LCA1 an excellent candidate for gene therapy. So excitingly, Shannon reported that 9 patients of the 15 who were treated in this clinical trial, these are the 9 patients who received the high dose of the treatment, had improvements in both a mobility course and general retinal sensitivity as measured by full field sensitivity. So excellent results, especially for a phase 1/2 where we're really focused on safety. And there was one news report that came out of Oregon, if I remember, that one girl treated in the trial, a young girl, was able to see snowflakes for the first time. So these are the results and anecdotes that we get really excited about. And so now Etsena is in communication with the FDA about designing and launching the phase 2/3 clinical trial. So hopefully we can move this across the finish line and get FDA approval. Now, just after ARVO, Etsena got authorization from the FDA to launch a clinical trial for an X-linked retinoschisis gene therapy. And we're very excited about that. Stay tuned as they talk about when that trial will actually begin. And what will be a new technology implemented in this gene therapy trial is this quote unquote spreading vector that Shannon has developed. This is a new human engineered virus. It's an AAV, but we think this technology may be even better than current viral vectors that are being used in gene therapy trials. That's because, as the name implies, it spreads more widely in the retina. So you can treat more retina with a single injection. And that also means that you can inject further away from the center of the retina where the fragile foveal area is and keep that area safer. You're not putting it in as much risk as you would if you were injecting near that foveal region. Because you can inject further away and still get the vector there, we think this will be safer. That's Shannon's, what Shannon's research has showed. And finally, Etsena is also developing a dual vector AAV for the treatment of Usher syndrome type 1B. This is still in preclinical phase. They're making progress there, and stay tuned as they announce more results and progress toward the clinic for that. So great news from Etsena. Okay, so now I want to revert back to a discussion of what I called earlier traditional optogenetic therapies. I think it's kind of funny that I say traditional optogenetic therapies. This is still a very new technology. 6-7 years ago, this wasn't even on our radar, but it's becoming a widely developed approach to restoring vision for people with advanced retinal disease. So anyway, the company Nanoscope reported quite a bit on their phase 2 clinical trial, their phase 2b clinical trial for people with advanced RP. They also have a clinical trial that's hasn't been underway quite as long for Stargardt disease, and I'll comment about that as well. So what Nanoscope is doing in their trial is they are delivering their treatment to bipolar cells to bestow light sensitivity to those cells, and again, have those bipolar cells work like a backup system for people who have lost a lot of rods and cones. Now, their optogenetic treatment uses what they call a multi-characteristic opsin. It's a protein that responds to natural light, so they don't believe goggles or glasses or something to amplify the light will be needed in this particular trial. And so they've reported on 27 patients, 18 received the actual therapy, 9 got a sham treatment. And what they reported is 16 of 18 patients were able to, under reduced lighting, either better navigate a very simple Y mobility course, either going to the left or the right based on where the light is shining, and or identifying one of 3 shapes: a ball, a cube, or a triangle, like a cone-shaped thing. So this is very rudimentary, simple vision restoration. But again, people are coming into this trial with very little vision left. Now, they also reported that 7 of 18 patients had improved visual acuity, at least 3 lines on what we call the Freiberg chart. And let me explain what that chart is. So when you go to the doctor's office and you're reading lines on an eye chart, you're looking at the Snellen chart, and that has all the letters of the alphabet, and they get smaller as you go. That kind of chart really doesn't work for people with advanced vision loss. A better approach is the Freiberg chart, and I have an example of a couple lines from the Freiberg chart in the bottom right here. And instead of having a bunch of different letters, either you have one specific letter like an E, or you might have objects that are oriented in different ways to measure somebody's visual acuity. On this particular Freiberg example, there's the letter E, and on the top line, it's oriented normally, and then the E is kind of on its back, if you will. And then on the second line, the E is pointed the opposite way than it's normally pointed, and then pointed down. So a person's ability to perceive the orientation of the E is the actual test. So that's, I think, encouraging that 7 of 18 patients gained 3 lines of vision on the Freiberg chart. Now, finally, as I mentioned, they do also have a trial for people with Stargardt disease. They've treated, I believe, 6 patients. They haven't reported officially on the trial, but they did show a video of a woman who runs a nursery, a plant nursery, and she was able to do some activities more easily after getting the treatment, like using a calculator and caring for her plants and things like that. So Nanoscope, now that they've completed the phase 2b, they're going back to the FDA to see what the next step will be. And likely, I think they will move into the a next phase clinical trial, a phase 3 pivotal trial, to see if they can get approval. I think their hope was that they might even be able to get approval with this data, but this might not be enough. So again, optogenetics, a very exciting approach for people with advanced retinal disease. And last thing I'll emphasize is it is gene agnostic. This is a gene therapy, but it's designed to work regardless of the mutated gene causing the disease. Now, another encouraging report for what I call an optogenetic-like therapy came from the company Kiora. Now, they too are working to bestow light sensitivity to cells in the retina that are normally not light sensitive. Again, for people who've lost all or most of their rods and cones. But unlike nanoscope and some of the other optogenetic therapies that are delivering a gene to provide the light sensitivity, Kiora is using a chemical, and they call this a photo switch. So this chemical was developed in the lab of a researcher named Richard Kramer at UC Berkeley. We provided Dr. Kramer with a lot of funding to pick the best chemical to do this. And at ARVO, Kiora reported, again, for 6 patients in their phase 1/2 clinical trial, all 6 patients had advanced RP. They had bare light perception or worse, no light perception. And at the time they reported the results, they had only administered the low dose. And patients reported, all of them, that they could perceive light better and contrast better. One gentleman was able to see his wife's cell phone. Now, I don't think he was reading the text on the cell phone, but he could see her using the cell phone. So this is still early. I want to make that clear. They're still at the low dose. It'll be interesting to see if they get better vision delivered to patients as this moves forward. Now, another key difference this optogenetic therapy has versus the others is because it's a chemical, you have to re-inject it. And in this clinical trial, they believe they will need to re-inject on about a monthly basis. So not the most convenient way to administer a therapy. This would be injected into the vitreous in the middle of the eye. We do a lot of that for wet AMD, but obviously you would want a more convenient therapeutic approach. And I think, not to speak for Kiora, but if this chemical works pretty well, I think they will explore and try to find better ways to deliver the chemical to reduce that treatment burden. But one thing I will say, one advantage of using a chemical that washes out is that you can develop better chemicals to replace the older ones, and a patient can get a chemical upgrade, a photo switch upgrade, because again, these wash out of the eye. And so a patient could decide to try something new, perhaps a new chemical developed by Kiora or a new photo switch developed by another company. So that is an advantage of using a photo switch, a chemical. You can easily upgrade. So stay tuned to our website as Kiora reports additional results. And finally, to close things out, I wanted to talk about an update that we heard from JSite, from Henry Claassen. And actually, for any of you that were able to attend our national chapter webinar last Saturday, Henry gave a nice talk on the progress being made at JSite. So this JSite has developed a cell-based therapy. We call these cells retinal progenitors. And the idea here is these cells are injected into the middle of the eye, into the vitreous. And the idea is these cells release growth factors or proteins to keep the existing retina healthy and slow or prevent degeneration. And we call this approach neuroprotective. It's protecting the existing retinal tissue. This is not replacing lost cells. This is simply keeping existing cells alive. And again, the cells that are injected release these growth factors that are neuroprotective. And as Henry says, this is like a gene agnostic living factory of retinal neurotrophic factors. This is gene agnostic. He's studying it, or the clinical trials evaluating it in people with RP and some related retinal conditions. And I will note that the cells that are being injected as retinal progenitors, they're not stem cells really anymore, because they've differentiated to almost become photoreceptors. But as progenitors, they're not quite there yet. And he feels these are the ideal cells for delivering these neurotrophic factors. So in the phase 2b trial, and these results were reported some time ago. In this trial for 85 people, he noted that nearly 40% of patients had improvement in their visual acuity, their best corrected visual acuity of at least 10 letters or 2 lines on an eye chart. And what's interesting is, again, the idea behind this therapy is to preserve vision. The fact that so many patients actually had improvement, I think, is really encouraging news. Now, what they observed, what Henry and his colleagues observed, is that people who began the trial with better vision had better results. So JSITE is now kind of quietly exploring a phase 3 trial. They haven't come out and given any details for one just quite yet. But I think what you'll see is they'll probably enroll people with better vision because that's where they're going to get the better results. And a final comment is these cells do not last forever. They last, Henry estimates, about 18 months. So they will need to be re-injected. They do go away and you can inject new ones. And they've done redosing in the clinical trials. So they know it's safe and redosing has been successful. So that's an update from JSITE. And that, friends, concludes the ARVO update. And I think we still have some time for questions.
We have a good 15 minutes. If you want to close the screen and we'll have Amanda highlight just you, that would be wonderful. I can't believe that's it. That's all you got out of ARVO? Just kidding.
Dun-dun-dun.
I know. We're gonna take this show on the
Well,
road.
I'll reiterate, and I'm going to find this as I'm answering questions, that the summary that yours truly did of the pre-ARVO summit gives a lot of detail on a lot of projects, including a lot of the things that I've talked about today.
Yes. And we can share that whenever it's ready, and we'll share the recording in case people want to hear you again. But who has a question? What didn't Ben touch on? Oh, Mindy has a question. Let's do it. And if you're not comfortable speaking up, shoot me a chat and I can read it. But I think, I'm guessing you can ask your question, Mindy. Good.
Great. Wow. Always something new, Ben. Unbelievable. Thank you for this great talk, first of all. Question for you. I know that with the optogenetics, the ganglion cells are underneath the photoreceptor cells. When you were talking about the optogenetics that deals with the bipolar cells, where are those bipolar cells?
So that's a great question, Mindy. And if you think of the retina, the slices of the retina, if you will, at the very top, at the outermost portion of the retina are RPE cells. Those provide support to the rods and cones. And next you have the rods and cones. Then below the rods and cones are the bipolar cells. Then the bipolar cells below them are the ganglion cells. And then the ganglion cells connect to the optic nerve. So that's how the visual information flows. It starts at the photoreceptors. Photoreceptors send the information through bipolar. Bipolar go through the ganglion cells and out the optic nerve. And there's different processing at each stage. And what researchers believe is the further up that chain you go, the better visual restoration, at least theoretically, you might have. So that's why targeting cones, these dormant cones, might be the best way to go.
Thank you. It's all exciting.
I have a question.
Oh, I was going to say David Tattle, Judge Tattle, and then the Wallsteins. That's the order I have right now. So it's all, you're up.
I am
Thank
up.
you, Ben.
Oh, David.
Ben, that was really interesting and very exciting. I have a question which is probably very elementary, but it has to do with gene replacement and CRISPR. Gene replacement, as I understand it, involves inserting a healthy gene with using a virus to insert a healthy gene into the retina. CRISPR-Cas9, does that also include adding a gene, or does it? I understand it cuts out part of the DNA, but does it replace the gene? How does this work?
So that's a great question.
I just don't understand that.
Sure. So in gene replacement, we often call it gene augmentation, but yeah, gene replacement, gene augmentation. But with CRISPR, what you're doing is there are 2 or 3 main functions of CRISPR. One is to locate the mutated region in the gene. That's the first part. The second part is to snip out the bad area, the mutated region. And genes have the ability, once you snip out the bad region, to recombine into a normal situation. So you don't necessarily have to add in anything. But in some cases, you can also deliver a new genetic sequence if that's what needs to be done.
So when you say CRISPR eliminates the region where the mutation is, does that mean it will snip out dozens or hundreds of base pairs where the mutation is?
So
Or does it just take
that's a-
that single base pair? How does it do that? I mean,
Yeah.
not how, but
That's a great question, and it depends on the technology. So some forms of CRISPR are really just targeting one letter.
uh-huh.
Others are targeting bigger regions. I know in the LCA10, it's targeting, I don't know offhand how big the region is, but it's not one letter. It's a bigger region than just one letter. It's a pseudo exon that's kind of a longer story for another day, but that's targeting a bigger region. But there are base editors that all they're doing is switching really one letter. They're not even cutting, they're just changing one letter to another letter.
So they're actually correcting the misspelling. Is that right?
Exactly, the base editors.
They're actually and presumably that would make that gene function again, right?
Correct.
I mean, that's totally unbelievably amazing. Thanks, Ben. That's very
Sure.
helpful.
Sure.
Science is so cool. All right, Wallston.
Okay. Thanks, Ben. That was really excellent. My question concerns your first slide from Heinrich Scholl, the resurrection of dormant cones. And you had mentioned this was done with RP patients. So I'm wondering if the fact of non-functioning but dormant cones is only characteristic of RP, or is that also characteristic of other IRDs in particular regards?
I have to say, that's a great question, Tom, and I am not sure offhand if that's the case with other retinal conditions. I will endeavor to get an answer to that question, if we know.
Okay, great. Thank you, Ben.
Sure.
Okay, see you. Oh, well, we'll say you're.
Thanks. Scott chatted me a question, Ben, wanting to know if these trials are on the clinicaltrials.gov site, and is that the best way to see if people could be a candidate? I already gave a plug for my retina tracker over chat, but I wondered if you could answer that and then maybe give people a little direction.
Sure. So there are a couple ways you can learn about these trials. Clinicaltrials.gov is a great way to get all the details for all the trials that I've discussed today. It can be a little cryptic. You can search by disease and then keywords, and you can get a lot more information than what you might want, but the information is generally complete and generally accurate. And then we also have a clinical trial pipeline chart on our website that provides more of a summary of what's underway. But the nice thing about clinicaltrials.gov is you can see all the inclusion and exclusion criteria. You can also see where the trial sites are to see if there's one that's convenient for you. And again, all that criteria for participation.
Great. Thanks, Ben. Any other thoughts, comments? Something?
Yes, I
Ben
had a
didn't?
question.
Please.
Mel Fayoun here. And I was wondering if the J-site technology could be adapted so that it would provide the photo switch chemical, which the Kiora treatment uses on an ongoing basis.
Yeah, that's a really interesting question. I think the short answer is not to speak for Kiora, because I'm sure they have their ideas, but the preferred way to do this might be with a gel or maybe even some kind of fat or lipid that provides slow release of the chemical. They probably wouldn't do that with a cell. A cell can release proteins really well, not so much a chemical.
Thank you.
Sure.
Great presentation.
Thank you.
Wonderful. All right. We can all just sit. Oh, thank you, Ben. Ben just added to the chat.
Well, I think it might have just gone to you. I was trying to get
Oh,
it to everybody.
Just kidding. Surprise chat for
Can-
me,
can you-
everyone.
Can you forward that? For some reason,
Yes.
I'm having trouble.
We will be able to, hold on, let me do this. If I can send it to everyone, and then we'll be able to also email it out. But I just sent it to everyone.
Thank you.
So you should be able to see. And again, Ben's notes make everything very accessible.
So again, this is the summit that happened before ARVO. But there are about 30 projects, and it's Sina's work, the cone-based optogenetics, Gene Bennett's work, the nanoscope work. A lot of this, the J-site work, was all covered at that summit.
What, can I ask a quick question?
Of course you can. Introduce yourself too, in case people don't know
This
you.
is Wendy Dwyer. I'm a major gifts officer, and I have several friends here on the call. So this is very, very personal to me, all of this. And I was wondering that Gene Bennett's, the virtual reality maze, could that be applied to a lot? There's so many of these clinical trials that the bar is so high of improving it by 3 lines on the chart. Could this, really change how clinical trials are judged in general, like overall, not just with LCA, but in USH2A and other clinical trials?
I think that's the hope, and I will confess, I don't know the details of how you configure or implement virtual reality for each scenario, but it's so adaptable and modifiable that you would hope that it would have a lot of flexibility, but yet precision to meet the FDA's requirements. But I don't want to say any more beyond that, because I really don't know. But, what I do know is Gene Bennett is developing it. And if there's anybody who understands what one needs to do to design an endpoint, it's her. So that gives me a lot of hope and confidence that this could be a really powerful tool. Hence, that's why I included it in this talk.
Thank you. Thanks.
Good. And Ben, one other question that came over chat was, can dormant cones be identified through a clinical test?
Yes, so I believe that they are relatively, maybe I shouldn't use the word relatively easy, but I believe that you can see these through some standard tests like optical coherence tomography. You can see where there's inner segments without outer segments. I know with adaptive optics, you could definitely see them as well, but yes, they're observable. That's an important element of this. You have to be able to see if somebody has dormant cones left if you're going to put them in a trial for such a technology.
Yeah, that's a great question. Okay, any final thoughts, questions, comments before we sign off for the evening on the East Coast? Is that another hand?
Could I ask a follow-up to Ben's last comment about identifying a dormant cone as opposed to one that is dead, if you will? Is there like a place you can go, or is there some sort of standard technology where one can go to find out what their situation might be?
And that's a great question, David. I honestly don't know the precise answer, but I think if through an OCT and the right retinal doctor, you may be able to determine that.
Sparing now.
So it'd be best to just talk to your current practitioner and.
Well, I wouldn't talk to just any practitioner, but like Mandeep Singh at Wilmer, for example, I think he would be able to.
Okay, yeah, we just saw Mandeep. He was a speaker at our vision wall.
Okay, wonderful.
Would sparing know, Ben?
Let me send that question out to Dan Chung at Sparing Vision, because he would know.
He would know. Dan
Given
knows
they're
everything.
developing that technology.
Thanks, Ben.
Oh, thank you so much.
Absolutely. Thank you, Ben, for sharing all of this and for representing us so well in New Orleans. Everyone will be in touch with the recording and everything else you need, but any questions, you can reach out and we would be happy, if we can't answer them, to go directly to Ben to get the answer.
Thank you, Ben. It was really great.
Bye. Thank you, everybody, for being on. Thank you.
And Wendy, thank you for the invite.
Thank
Thank
you.
guys.
Thank you all.
Wonderful seeing everyone. Bye. Thank you.
Bye-bye.
Bye, guys.
Bye.
Thank you, bye.
Bye. Goodbye.
Bye-bye.